Okay.
All right. So if you notice on the title, this is titled Biostat 101, sort of, but not really. And the reason for that is when Jay first contacted me about teaching a biostat, I thought, it's probably not going to work because how much biostat can you teach in 40 minutes? So instead, we put together this two-part series. The first part is basically how do you work with a statistician? What do you need to do to get ready to reach out to whoever you're going to use as a statistician, and how will that statistician work with you through the process? So there's a lot of things that we'll be talking about in terms of preparation to help keep you out of trouble later. So that's really the emphasis for today. Part two, which I hope to start today, because part two is a lot bigger and I want more time later for it, is really based on here's some examples out of reports that I've generated. What do they mean to you? When you look at this stuff, when you look at my report, how do you read it? You know, I thought those two things would probably be two of the most important things that I could give you in just two short periods. Okay, so Jay, if you can scroll up a little bit. If you have the PDF, these are all working links to jump to different sections. I did want to point out a typo right here. When I did this, I didn't mean to put a two-sample t-test as a subsection to chi-square. That was pretty dumb. It's a subsection, not a sub-subsection. I'd use LaTeX. If anybody speaks LaTeX, you know what I'm talking about there. This belongs in its own. I caught it, I was going to fix it, but then Jay's already set it out. It's going to change all the numbering, so I left it. But this is its own subsection, real minor thing there. All right, keep going. Okay, so why work with a statistician? If you see this graphic here, it says I can prove it or disprove it. Well, what do you want me to do? That's kind of the standard way people look at statisticians, you know. This is very true if your statistician's not ethical, all right? So just a little bit of humor there. The whole point behind working with a statistician is they're going to help guide you through the process. And I think of myself, while we're working that project, my part of the team is to act as a guide to help get you through the process to be able to answer your research question. Now, this next little quote down here, I'm going to scroll up just a little bit. By R.A. Fisher is one of my favorite all-time quotes. R.A. Fisher, if you've never heard of him, he's thought of as the grandfather of modern-day statistics. He died in, I think, 1962. He basically had his hand in almost everything that we do today. Gossett came up with the whole idea of the t-test based on beer from Guinness Brewery. Thank God for beer, we wouldn't have a t-test, right? But it was Fisher, when he got his hands on it, said, hey, this is important, that people started paying attention. And this quote by Fisher says, to consult a statistician after an experiment is finished is often merely to ask him to conduct a post-mortem examination. He can perhaps say what the experiment died of. That is so true. One of the worst or most frightening sentences ever from clients is, I have data, can you help me? All right, that is like, oh my God, here we go. Who knows what's gonna happen? Yeah, I should have been involved long before the I have data. There's been a lot of projects that simply crash and burn because the data wasn't collected correctly. So it was impossible to answer the question they were interested in with the way they did the data. So we're going to talk a lot about avoiding that. So early planning is really important. And that means you need to reach out to your statistician, whoever it is you're working with, prior to data collection. Again, that is so important. And this last little quote here, I'm not sure who said it, but it's always easier to steer a ship than to raise it off the ocean floor. And that is just so appropriate when situations where you already collected the data and then you go to a statistician and say, now I'm ready to analyze it. Now, if you have a lot of experience, you're probably in good shape. But if you're new to this, it can be horrific. So getting ready for your first meeting. To me, in my thinking, there's 4 questions that you need to address. You need to think about before you reach out and set that first meeting with your data analyst, whoever that's going to be. First, your research question. You'd be surprised how many times I have phone or Zoom meetings and the folks I'm meeting with don't have a research question yet, right? If you can't put your research question into 1 or 2 simple English sentences so that I can understand it, then you're not ready to start. Now, having said that, there have been situations where folks getting into the first project, they have a good idea of what they kind of sort of want, but they don't know enough about data analysis. They don't know what's possible with the data. So they really can't formulate it until we have a sit down. Well, that's fine. Nothing wrong with that. But if you're kind of clueless, saying, hey, I've got some data, can we find a question? That's totally backwards. You want to avoid that at all costs. The second thing here is this is actually more important than you may think. Why are you doing this project? A, I just need you to graduate to get through a program. Okay. B, I have an interest in this area and there's little or no research that I can find. C, I was told I was going to do it. Those are the 3 primary reasons that I get. Now look at this, you think, well, B is the obvious answer, right? Well, no, they all are. And they're actually all legit. I mean, I totally get it. Not everybody I work with has a real desire to do analysis. They need it as part of the program. And that's cool. I just need to know where you're coming from. The next thing is a hypothesis statement. This is really important, if possible, because the hypothesis statement will help guide me in how I perform some of the analysis. The hypothesis statement is simply what you think the results will be. If you're doing a case control study and you think the case patients are going to show improvement in some way, then you need to define what improvement means. Because what tells me in the back end, so to speak, am I doing 1 or 2 tailed tests? Because if you know the direction ahead of time, 1 tailed tests are appropriate. If you don't, then 2 tailed tests are appropriate. Usually, you see in most literature, it's common to do 2 tailed tests because they're much more conservative. Well, okay, whatever. If you have a direction, what you'll probably see from me are both. You will see, here's your 1 tailed test, because you said this is the direction you're looking. This is the result looking in that direction. And here's the 2 tailed test, p-values. All right, so that way you can make a conclusion or decide for yourself exactly how you're going to end up putting this together. And the last is your cookbook, if possible. Or I'm sorry, code book, not cookbook. Your code book, if possible. Go scroll up and we'll talk about the code book. The code book probably should be called code sheet. Don't let the word book scare you. It's not like this big old huge thing you put together. It's extremely important, and literally within about the last month, I've decided I'm requiring a code book before actually starting the analysis. Because what the code book does, it does 2 things. Number 1, it forces you as a researcher to think even deeper about your research. Deeper about what these variables mean that you're collecting, why you're collecting them, and how you want to use them. And number 2, it's a roadmap for me. I've realized I spend a lot of hours kind of chasing my tail, guessing based on the data and producing stuff and reports that nobody really cares about. So let's just narrow it down to what's important. The code book is really, really easy. It's just a list of all the variable names. What are you going to put in that heading on Excel? That's the variable name. What they mean, the meaning of them, what they measure, what the data will look like. This is really important. And what variables you want to compare them with. Are they simply descriptive demographics, or do you want them as actually part of the analytical part? So here's an example of a code book from another project. It's most of it. There's probably like 6 or 7 more variables, but I think you get the point. So sex. I need to know, are you recording male and female? In other words, at birth, their sex at birth, or are you listing one of the, I don't know, I think last I heard 92 gender identifications. You know, those 92 may be important for your project. I don't know. But we need to make sure we understand what's going on. Male and female, the 1s and 0s. This is extremely important. And it's not like it was 20 years ago. I would recommend, if you're recording male and female, that you record male and female. Record the word. Okay, not the 1s and 0s. If I need a 1 and a 0, I can, like in 30 seconds, boom, change everything into a 1 and 0 and another variable that I use for the analysis. Okay. The problem is, and this has happened about 3 years ago, I guess it's sexist for female to be 0, male to be 1, so somebody changed it on me. Well, it's fine, I don't care, but they didn't tell me, right? So one of the predictors was whether the hysterectomy had an impact on this particular thing they're measuring, and the hysterectomy for the males was extremely important. You get the idea? They're asking, what the hell's going on? Well, what's going on is I didn't know you switched males and females, right? So the 1s and 0s can be confusing sometimes, and more popular, they're becoming 1s and 2s. Well, I just changed all those to male and female anyway. So using the word there is probably the best way to go, so there's no doubt about it. Then over here, what was written is this descriptive, part of the demographics. They checked and see if it's for possible confounders. All right, that's kind of a common sort of thing you do with demographics anyway. Ethnicity, it's perfectly acceptable to say levels provided by Brian, and I'm going to show them to you in a few minutes. I've got a list I retained several years ago from Current Medical that is what they use in their computer, and I'm willing to bet it's the exact same thing that you guys probably use. And so I have that list, so every time I need it, I just grab it, drop it in, boom, done. And I've done it for several projects for Aventa so far, and it's been no problem so far. So just saying levels by Brian, and what are you going to use it for? Is it actually part of the analysis, or just descriptive and see if there's some confounding or something going on? Like age, you're going to measure in years, and that's a number. And again, what's going on here? The case and control, everywhere I have 1s and 0s, it's because that's traditionally what's done, but I would still recommend the word, not the numbers. Now, years ago, 20 years ago, you couldn't do that. The computers could only use numbers, so everything had to be coded. But today, you can put in a word. Well, you get the idea. It describes the variable name, so I know what it is when I load it up. I have an idea what it's actually describing. If you need more description here, go ahead, put it in. It's not a problem. And what the data is going to look like, because that gives me an idea of what's known as a measurement scale. The measurement scale tells me what kind of analysis I can and can't do. So that's what's kind of important here. Coxies, it used to be the Coxie tires always came up as 1/2, 1/4, 1/8, 1/16, but working with a 1/2, it doesn't work. All right, so we just use the denominator because we all know what that means. All right, it's all based really on the denominator anyway. And here it says, not sure if we will use this. That's a good point. It's not uncommon for me to get data set that has 20 variables in it, but we're focusing on 7. Well, leave those other 13 in there. All right, it's better to have it and not use it than go, oh my God, I got to go back and try to find that again. All right, and if you're just saying here, I'm not sure if we're going to use it, well, fine. That tells me I don't have to worry about it for today. Okay, now this code book, or one of the things the code book does is it helps tell me what comparisons to make. But don't think for a second that you're somehow limited to those comparisons, because you're not. That's nothing more than a starting point. That's it. It gives me a roadmap to start with. And the way all these projects typically work is I'll generate a report, I'll ship it off to you. You look at it, you get comments, I'll generate version 2, ship it off to you. It's not uncommon to go through 5, 6, 8, 9, right? I've been working on a project with a doctor up at Current Medical 4 years, I think the last 4 years. And there's nothing in the literature on this particular topic, absolutely nothing. And almost every year he comes back to me for another look at it in a different way. And I think I'm on like version 16 or 17 of the report. You know, that's not a big deal. All right, so don't think that anything you give me in a code book or anything you present on day 1 is it. It's just a starting point. That's all. So it's not uncommon to change a code book at all as we're going along, because one of the issues that will happen, and we'll talk about it on our face-to-face, is if you may have 13 different drugs, right, that you need to list. That's a lot. Breaking any data into 13 categories means you have a lot of data. So yes, start with that, but what I'm going to tell you is to think of later on, can these 13 be combined in some way? They have characteristics that make sense to reduce it to 3, 4, 5, 6. All right, so the code book would change as soon as that happened. Not a big deal. Okay, we can keep going from there. All right, collecting and recording data. This is where most research projects die, because it didn't happen right to begin with. And when we have our face-to-face, or you have your first face-to-face with whoever you're working with, this has to be an extremely important part of the conversation to make sure you're all heading down the right path. It's got to be recorded in a way that lends itself to proper analysis. And that's my job, to make sure that you have that set up. And what I always say, and I already alluded to it, is go wide. Right? Remember those 27 variables, whatever, but you only go work with 6 or 7? Okay, go wide. And I go wide in a couple different ways. Number one, if the data is there now, grab it. If your IRB will let you have it, right? And if you don't use it, fine. And the other way to go wide is, like example, collect age as actual age. Don't categorize. If you categorize age as young, medium, old, or whatever, guess what? You can't go back. It's impossible now for me to give you an average age. It's impossible now for me to use it as a continuous variable linear regression or anything like that. It's impossible. So if you give me the actual age, same thing with stuff like BMI. Well, if you're looking through medical reports and you're going to use BMI and BMI is within there, that's fine. But don't calculate BMI if it's not. Give me the height and weight and just tell me what units you're in, right? So I can, in 30 seconds, write a line of script to calculate BMI. And then we can always go back if you needed to use just the weight for some reason or just the height for some reason. You never know what's going to happen. And don't categorize BMI, right? I know there's a 4 or 5, depends on what list you look at, categorization for BMI. Let me do that. Again, you can't go back. If you give me the categories, you can never get the numbers back. And it may be, and we'll talk about in part 2, an RLC analysis where it may be you have BMI and you're looking for a threshold point where something seems to happen. Well, guess what? That's not happening if you categorized it. If you left it numerically and there's something there, looking at the AUC, the area under the curve for sensitivity, maximizing sensitivity and specificity can give you a threshold where maybe this would break. As an example, if you took, Coxy, yes or no, typically that's 4 or greater on the titers, right? If I remember right. Well, we all know that, but if I already have all the titer numbers there and then do an RLC on the titer numbers, determine Coxy, I'll bet you a pizza 4 is going to pop up. See what I'm saying? But what if you're in an area that you don't know 4 is the answer? There's your RLC that help you figure out where that threshold point where something seems to happen. Can't do it if it's categorical. Trimesters. Everybody knows what a trimester is. I couldn't tell you the actual days on trimester. I could look it up. But if it's available and you're working with trimesters, use days. Because again, what if something happened in the second trimester? If you're categorized, that's all we can tell you. We couldn't tell you if it happened late in the second trimester or early because you don't have the days. All right, so that's the other way when I say go wide. Go wide in terms of number of your variables and go wide in terms of the values you're collecting. It's always easy to condense, but if you give it to me condensed, again, you can't go back. All right, go ahead. Here's another one. This was actually out of a study I did several years ago at Current Medical. When you enter data and you're typing data, there's all kinds of mistakes you can make. This research actually had an ethnicity, had Hispanic with a capital H, as you see here twice. And these two are actually different. Had Hispanic with a lowercase h, had HISP, Hispanico. And you know if there's Hispanico, there's Hispanica, right? It's got to be. I don't speak Spanish, but I will bet you a pizza, Hispanico and Hispanica aren't even words. But honest to God, it was listed like that, right? I'm going, what the heck? So the key here is like the capital H and lowercase h. The computer right now sees 1, 2, 3, 4, 5, 6 different entries for the same thing. That's bad. And you probably, or I can guarantee you can't see the difference between these, but you could probably figure it out. One of them had a blank space after it. Do you know how hard that is to find? I actually had one once that had 1, 2, and 3 blank spaces. So it wasn't Hispanic, it was something else, but it was like, you got to be kidding me. Why is that same word spelled the same way showing up 4 different ways? Right? And trying to track down 1 and 2, 3 blank spaces, oh my God. I was really thrilled about that one. So we really want to avoid that as much as possible. And we're going to get into exactly how to avoid it. Another common and serious data collection issue is, again, in typing, you have to type numerical data. There's just no way around that. Like here, this came out of another study, 11/6, 11.8. I bet you that's supposed to be 11.6. It's just a typo, right? But I'm not changing it. I'm shipping it back to you to figure out what it should be. I'm not changing stuff like that. The NAs are a problem because capital NA, lowercase n/a, capital N/lower a, it's all different to the computer. It sees it as a different variable name. Now, for the NAs, I do have this line of code here that looks for the most popular entries for NA. Blank, nothing there at all. Capital NA, N/A, NA, unknown, a dot, a dash, 1 asterisk, 2 asterisks, 3 asterisks. Those seem to be the most popular ones. So I can filter those out right away when I read the data and change it to what the computer looks at as 1. But it'd be better if we catch it to begin with. This guy is a serious problem. And I know you've all seen it because that's the way stuff come back from the lab on certain things, right? Tighter something, I think, say like less than 4 or less than 2 or something like that. That's not a number. So what's going to happen, and that's important in the code book, we start talking about what the day is going to look like. Hopefully you'll foresee that's a possibility. So what's going to happen is we're going to have to talk about that. If you want a numerical analysis, you need to come up with a number that makes sense. I would say leave it in initially, but alert me that it's there. And it may be that a 1.5 makes numerical sense to put in there, or a 1, or a 0.5, or even a 0, I don't know. That's on your end. You have to decide what makes more sense clinically. But you cannot do any numerical analysis with these numbers with that less than, because it's now a character. It's the same as a word. May as well be Bob. I mean, it really makes no difference at all. So that's an issue. If you can catch it beforehand, like during our sit down, our face-to-face meeting, that's great. If not, it's going to show up, and then I'll get a hold of you. Okay, go ahead. Now, this is a quick and easy way to solve this. Here's some instructions so you can do it by yourself if you want. When you create your Excel file, I just had last week, spent about 40 minutes online in Zoom creating this for somebody over at Career Medical. Not a problem. You know, they had the list of variables, but they just didn't feel comfortable with this. So I can do it for you. It's not a big deal. So like an ethnicity, you put the name of the variable here, and then up here, where it says data, it kind of got cut off. Select data, and then under data, select validation. It defaults to any value. Change it to list, and then I just copy and paste that list of ethnicity I have. Hit OK. And now when I go to ethnicity, I see the little down arrow. When I click on it, there they all are. Everybody's spelled the same. There's no misspellings. It's really important when you're entering different conditions, because I can't pronounce 99% of the conditions that you guys work with and the drugs you work with, but they got to be spelled the same. So if you can put them in a list, even if it's long, hopefully alphabetized or something to make it easier to find something in a list, that will ensure they're all spelled the same. And we don't get that issue of a bunch of different garbled stuff in there. Same thing for like gender, data validation, change it to a list, male, female. And I put unknown in here just for sake of. You may want to put an NA in there. If an NA is possible, then on all of these, you could put an NA so that it's all the same NA, right? And then again, when you hit that down arrow, you're going to get your choices. So it's nice and clean. There's no misspelled words. Everything that means the same thing is actually the same, okay? Okay, so I wanted to get through just two pieces of the part 2 data analysis discussion, because when we do the second part, there's a bunch in there. And no, I'm going to need every minute probably have during that presentation, and we're going to be done pretty quick here. With only a few people physically here, nobody asking questions, we're going to fly through this sucker so you get more lunchtime or whatever. But there are two concepts that I want to talk about. The first thing is effect size. Now, effect size, if you start reading about it, I can find articles on NIH that tell you how important effect size is. I can also find articles at NIH that tell you how screwed up they are. It's kind of a problem. So let's jump down a little bit, and I want to keep going right there. So the whole idea behind effect size is actually trying to find a number that describes the practical, or commonly referred to in this line of work as clinical significance. All right, so they're trying to take a number, a standardized value typically, and say this is going to tell you how important the result is. And that's where the problem comes in. As an example, let's just say we're working with diabetes patients. We have case and control, and they were given some whatever treatment, and the control group started with an average A1C of 8.4. And at the end of whatever your period was, they dropped down to 8.3. Okay? Your experimental group, they also started at 8.4, but they dropped to 8.25. So the difference is a 0.5, right? That would have an extremely, extremely small effect size. And then you'd have to decide, is that 0.5 actually mean anything? But put it in another context. Suppose they started out at 8.6 and dropped down to 8.25. The difference at the end was still that 0.5, which now doesn't mean anything. It's how much they traveled. You follow me? Well, the effect size is still probably showing up as being pretty small. But clinically, it's going from, 8.6 to 8.25. Is that important? Is that a big deal? Well, I don't know. That's something for you to decide. All right, or maybe simply did they get into the 7s is what you're using as a benchmark, right? Which completely changes the analysis, but still. An effect size is the number that tries to tell you whether your observed difference, that's really what the effect is, whether your observed difference is small, medium, or large. And the general interpretation, which is a problem, is that a small effect is typically not that important. A medium effect is kind of important, and a large effect is extremely important. Well, without the context, I don't think those numbers actually mean anything. Now, there's a bunch of different effect sizes. Cohen's d is probably most common. It's used between two groups, typically the means between two groups. Now, Cohen, this came out in his book in 1988, when he wrote a book on power analysis for the psychological studies. And in his book and in other papers, he said, hey, look, I have these boundaries or these ranges that I define: small effect, medium effect, large effect, right? And even then he said, this only makes sense in the psychological studies. But everybody and their brother is using Cohen's D's for everything, right? It's still a standardized number, so there's something to say about that. But the interpretation of that standardized number can really get murky. Cohen's H. Oh, and you see me report Cohen's D quite often, and Cohen's H. Cohen's H is a better representation for odds ratios and relative risks, is kind of what the literature says. It's an odds ratio itself is actually an effect size. That's a legitimate effect size. The difference of two means is not. It has to be standardized. It's literally the difference divided by the pooled standard deviation. There's your effect size, basically. An odds ratio is an effect size by itself, but still quite often they're reported. Hedges G or Cohen's D, Cohen's H or Cohen's D is used to describe the effect size in a standardized scale for the odds ratios. And I don't want to get into the weeds and the math, but Cohen's H takes the arc sine of the value, multiplies it by 2, which gives it a range of like 0 to 2 pi, and then they break it up. So why? I don't know. But that's what's going on with the effect size stuff. Hedges G is actually the same as Cohen's D with a minor adjustment to it for small sample sizes. See, one thing in statistics is when somebody comes up with a new measurement, everybody and their brother tries to improve on it so they can publish. And then a lot of these improvements really don't mean anything. That's just the way it is. There's several other measurements of effect size. Now, a lot of publications are requiring effect size, whether you like them or not, to publish. So I've been putting more and more often in my report, I drop in which effect size was calculated and what the value was. So you'll have it. If you're trying to publish and they say, where's your effect size? Well, here it is. Or you may want to put it to begin with to take care of that bullet before it ever gets to you. Pearson's correlations, odds ratios, and relative risk, these are all actually effect size by themselves. But again, they're commonly standardized for publication. Now, the thing that does do is it allows to compare effect sizes from different studies. So there are positives to it. It's just the big question in my mind is always, how legit is that effect size to begin with? And all these effect sizes with a little bit of algebra can be converted to each other, which is common for if you're doing a meta-analysis. Very common in meta-analysis, they'll settle on one effect size, even though multiple others may have been used in different studies, convert it to the one they studied on or settled on, and then do the meta-analysis based on that effect size. But again, the key here is that the effect size is just an attempt to numerically quantify how significant in a clinical aspect. Now, p-values don't do that. It's important you understand the p-value. P-value tells you nothing at all about how important your research is. Zero. And that's something that people have a tough time with. They think if I have that almighty less than 5% p-value, then I'm good to go. Well, I don't want to pop your bubble, but I wonder if anybody knows where that 5% came from. That 5% came from Fisher in the early 1900s from a lady in England who said she could tell the difference between tea if milk was poured into it or if milk had tea poured into it, which way it was poured. Okay? Now, first of all, who the hell cares? All right? It's kind of like James Bond shaken but not stirred sort of thing. You know, who really cares? But because of that, Fisher came up with this idea of 5% error was important enough to be considered legit if you got less than that. It's kind of like the boundary. And Fisher himself said that p-value is not the end game. It's the beginning of it all. A significant p-value just says, hey, I may have something real here. Because really, numerically, all p-value does is the probability of what you're observing, the difference, the result you're observing, being by chance or real. Nothing there tells you how important it is. Zero. Okay, let's go ahead and scroll down a little bit. Here's another thing I want to talk about a little bit about is you see in my reports, quite often you say that, I'll say that I use permutation or bootstrapping for this particular analysis. Now this graphic it's a simple graphic, but I think it does an excellent job, if you know what you're looking at, of explaining what bootstrapping and permutation tests actually are. So first of all, the number one assumption of all data analysis, everything, I don't care what you're doing, the number one assumption is that whatever data you collected looks like or is representative of the population you want to talk about. That's number one. If you can't convince yourself that's probably real, then you shouldn't even be doing the analysis because you don't have anything that's worth anything. The only value there would be is describing your data, but there would be no generalization anywhere. So that's number one. So in the blue here represents the typical analysis. The big box is the population, the little box is the sample. Now, there are certain things that for a t-test, we have to assume about that sample, and we can check it. And that's normality. We have to have the almighty bell curve, else the t-test doesn't work, because the means are assumed to come from a normal distribution. So if you're not normal, your results could be way off. And then there's stuff like the essential limit theorem that says if your sample size is big enough, and then big enough is defined by different people different ways, that the means will become normal, and that's true, right? So that's kind of your typical path to, like, for a t-test or something. Here is a bootstrapping or permutation idea. So I have the same population, I take this sample, the same thing, that sample better look like my population or it's not of any worth. Now up here, we calculated p-values based on this assumed distribution. Down here, if my original sample looks like my population, I can get multiple resamplings of the same size from here with replacement. So all these samples are different, right? Your original sample would be without replacement, then the bootstrap sample is with replacement. So what you're doing is you take a look at each of these, and each of these would be a minimum of 10,000, or sometimes go up as high as 200,000, because the computer can do it. And it builds distribution. This is what it looks like. This is what the actual distribution looks like. So I can calculate p-values based on a representation of the actual distribution and not just assumed normality. So some people use that all the time, don't even bother with t-tests. If they're going to do a t-test, it's based on bootstrapping. What I commonly do is, because everybody understands t-test better, is if I have an issue with the assumptions, then I will go ahead and I will do a bootstrap, and I will tell you in there that because of gross violations of the normality assumption, a bootstrapping of 100,000 or whatever I did that day was used, and this is the result. And what I've actually did to make my life easier is I don't run t-tests at all anymore. I have a script that I run every time that runs the t-test inside the script. It checks for normality. It gives me graphs of the data so I can take a look and see. If you look at the graph, you say, it's not normal. There's no way you could convince me that's normal. Even though the formal test said it might be normal, then I will go ahead and do a bootstrap, and the bootstrap is actually in the same script, so I get all that output in once. Everything's right there. And bottom line is, if the p-values are the same or so close to it, who cares? Then really probably didn't matter which technique you used, because you got the same result. As an example, let's scroll down a little bit. It's going to have to be quite a bit, I think. It's going to be into the next section or so. Keep going. One more right there. See, these are two density plots for the two variables, case and control. Case is the pink, and control is the blue. And is emission, and this value, this is actually out of a study I did, so I took out the values because they're actually working on publishing and so forth. I don't want to get in front of them. You know what I'm saying? So I took out whatever this actually means. There's no way you're going to convince me that this is a normal plot. It ain't happening. And actually down here, I even talk about this, a two-tailed permutation test was used because of the violation. Right? So it's that sort of thing that you will see from me. And we'll get into this in part 2, because anything when you're looking at the presentation, it has this dark blocks all around it. That's actual excerpt from a report somewhere. And that's what we're going to do as part 2, is go through all these or many of these different reports so you can understand what they mean. But anyway, yeah, that's not normal. That ain't happening. All right, you want to scroll back to where we were? Down this a little bit. Okay, right here, then I just go into pretended two-sample t-tests. This is a link that actually goes to an NIH paper about using bootstrapping is particularly effective in the SF36. I have no clue what that means. I don't know, but it doesn't matter. It's a good article. I read it, and it talks about bootstrapping in that field, so it's actually pretty good. It's common to see it because of violations of assumptions. When we have a violation of basic assumptions, like for chi-squared, one of the assumptions for chi-squared is none of the expected values can be 0. Well, that makes sense because the expected value squared is in the denominator. And you know 0 in the denominator blows things up, right? It's not a number. So everything comes to a screeching halt. So that makes sense. And then there's with a chi-squared, no more than 20% the expected values can be less than 5. That's a controversy. Some people say that 20% is hogwash. It should be none of them less than 5. Others say with all these different simulations, it doesn't matter if it's less than 5, as long as there's no zeros. So everybody's got their own opinion. So I kind of go by this. And if I have an issue with this, and then I will do a resampling thing, a bootstrap thing for your chi-squared. It also comes up to ANOVA, because the assumptions for ANOVA are almost identical to a t-test. And sometimes for linear regression. There's when you will commonly see the possibility of a bootstrapping by me. And I just want to introduce the idea of bootstrapping. So number one, you know it's legit. And why I'm doing it when I do it. Now, just as a side note, remember I told you that Fisher, when Gossett came up with the t-test, or the t-distribution, Fisher got all excited about it. Well, one of the reasons Fisher got excited about it is Fisher realized that the only way to get exact tests, you know, I'm sure you've heard a lot of exact tests with Fisher's name on it, is through permutations. That's the only way to really get it. Everything else is approximation. And what Fisher realized is that when Gossett came up with this formula, it's a mathematical formula that creates the t-distribution and calculates, you can calculate probabilities from it, is it was actually nothing more than a closed form mathematical formula that closely approximated the results of a permutation test. So all of a sudden we had a way to get close to the real way, the best way, according to Fisher, to calculate p-values. That's why he got all excited about the t-distribution. That's just a little history to hopefully help convince you that the whole idea behind bootstrap is legit. And bootstrapping is like a subset of permutations in many ways. And I don't want to go into much more detail on that because you don't care, obviously. So actually, that'll wrap it up for me. I don't know if you can hear anybody. If there's any questions, I can try to field some questions if you have them. The important thing, like I said, if you're reading through that presentation later, is that anything with this box is actually from a report. And we'll go through what all that means and how to interpret it in more detail whenever part 2 comes along. Jay's talking about trying to get it scheduled sometime. Yeah. Did this make sense to you guys? Did it seem useful? That's the key part. If it's not useful, then there's no reason for Jay to invite me back. Yeah?
Yeah. I think it was good to understand how, especially since we're working.
And it doesn't matter who you're working with, the same idea will carry over everywhere. If you have those 4 questions I talked about and at least start the code book, and you bring that to your first meeting with whatever statistician you're working with, they're going to love you. Yeah, they're going to know you got your act together. At least you're starting in that direction. Yeah. No questions? Everybody's good?
Any questions? So this, like I said, this is a two-part series. I'm going to have to schedule this sometime before September 9th. So look out for my invite. But Brian will go ahead and dive into more of the concepts he introduced today. But if there's no questions, I will bid you adieu. If you do have questions afterwards, feel free to email or Teams me. I can relay those questions to Brian. All right.
Yeah.
Thank you, Brian.
Sounds good.
Oh, there you go. Perfect timing. Yeah. All right. Thank you, guys. Have a good one.